Alright, ice secretion and the de-icing evaluation. Physical property of the ice secretion when the aircraft has been able to determine the physical property to result with the label of the property directive bearing with the effectiveness of the de-icing system, simply is not currently practical measure created for the flight. Represented ice formation study under laboratory conditions experiments have definitely determined the mechanical property created to ice and the strength required for the fracture over the ice in figure 3.1. One experiment for the ice generated with an introduced with a 20 micron diameter water to droplets high speed with a cold air stream and then impinging onto the cold metal plates. The ice density of 0.74 grams of centimeters cubed appears for the ice very similar to rime ice. Figure 3.2 of the appendix A, with the thickness of the ice level range from 3/4 to 1.5 millimeters. Test sample to consider that 1.5 millimeter thickness is a positive aluminum plate with a bowl stack with a 4-point bend loading of the figure 3.1 and the constant strain loading in the ice for a study with the determined strength required for the fracture of the ice. Static loading test to measure the Young's modulus of the elasticity of the ice layer with a recording instantaneous deflection when the samples upon with applying the load, stress relaxation due to the creep of the layer for the preventing fracture of the ice during static load. Dynamic load testing subject with the example of short initial acceleration performed and creep of the strain with a rate followed by a long period over the constant strain rate with a strain rate with applied with wear in range of 0.3 to 300 to 1300 to inch and inch second with a static Young modulus measure of the ice samples of 2.85 G pascals or 413,000 psi. Figure 3.1 shows the 4-point bend loading, a load point, a point support, ice, and aluminum plate. Result of the dynamic loading test explained with a simple logical of the model, and whereas in E1 instantaneous Young model, E2 with the extreme of the creep of the elastic module, and N2 with the viscosity creep factor with the parallel loop represented with the transit creep of the decrease of the strain rate with the polycrystalline ice at 1,350,000 psi. The test result at 551,000 psi and 400,046 psi a second. For this model, total strain can be expressed. The strain is where blank is strain and T is time, and the typical strain is method needed for fracturing to determine the testing with a 1.5 to 10 to the negative fourth inches over inch equation may be means with estimating the effectiveness of mechanical de-icing system. For example, the de-icing made model with a mechanical force versus time and the force function transmitted with the ice layer can be specified resultant strain exceed the empirical determined value of the stated above, the probable the ice shear of the de-icing results. Physical property of the ice or function formula information conditions. In these conditions, temperature will be found the most intensive of the variable, the temperature, effective shape, quantity, stress, accelerated the ice, and hence the aerodynamic property, propensity of shedding greatly reduced ambient temperature that may be associated with a reduced liquid water content, which affect the type of the ice and form of the other factors of the attitude of the aircraft, the velocity, water droplet size, in addition net accretion in function over the time and the icing conditions. Liquid water content, water droplet diameter do not have significant adverse characteristics, although show the rheological model of the dynamic load testing ice strength. Show the resistor 1 instantaneous electrolysis model is E2 the transistor creep ballistic model, and then the transistor creep decreasing strain rate and load. A slight reduction in ice strength will denote with the increase of the droplet diameter factor with the influencing shape of the character of the vibration change of the ambient condition and of the operation condition. This is particularly true with the rotating shift of the shedding may be deliberately induced. Computer analysis, ice and de-icing. The methodology proposed evaluating icing de-icing phenomena of the engine inlet valve with the following step of determining the flow field of the in and around the inlet, calculating water droplet inject trajectories, 3 calculating the amount of shape of the ice acceleration inlet structure of the 4 determine the trajectory of the shove of the ice fragments into the accelerated ice alter of the inlet geometry. More accurate solution requires reading steps 1 through 3 of the new geometry. Engine manufacturers can use information obtained with a way to predict potential damage areas. Figure 3.3 is the flow chart of the process. Show the computer codes of flow field analysis, computer codes, and empirical data, and that goes into inlet icing accretion, de-icing system, icing shedding characteristics, computer codes and empirical data, ice shedding trajectories into impact map. From ice shedding trajectories, it goes back to drop trajectory analysis and flow field analysis. Flow field analysis, computer codes, empirical data goes to inlet air ice accretion, back to flow field analysis, droplet trajectory analysis, inlet icing, de-icing cycle goes from inlet icing cycle in between the de-icing system and the computer and empirical data and the ice shedding characteristics. That's Figure 3.3 icing, de-icing, analyst flow chart. Flow field analysis. First step of the icing analysis to determine the flow field property around the turbine engine inlet. This can be done using the 3D computer codes available in the literature. Figure 3.7 and 2.3.13 provided here is a list extensively of 3 and D codes of the flow field analysis, most often well documented, available through the government over the commercial sources. Linear fuel potential 3D code transitic flow NASA. 2 criteria that are suggested by choosing the list above. The first for the code that produce the accurate velocity of the arbitrary points for the region of the body with its air speeds ranging from the subsonic to transonic, and second for the code with the validatively comparing with the predictable water droplet impact location of the experimental data. These criteria is currently met only with the rare near code, which has been extensively inlet flow field analysis. The code used with the flow field input chem introductory with the water droplet impingement analysis described in the following sections, which can be compared with new experimental water droplet impingement data now available. Reference 314. Unfortunately, rare code has been unavailable to general use. It has been a Boeing proprietary information, primary open literature source. The reference 315 essentially user manual does not give the proper program calculation details. By arrangement with the NASA Lewis, however, the program will become available in 1988. The Rainer code is not a standalone code, but require primary code setup of the inlet body geometry relate with the computation method of mathematical representation geometry computer language. Boeing proprietary setup code called the master modeling aerodynamic surface three-dimensional explicit of the representation give the precise surface definition consistent continuous first and second derivatives. Also defines all of the points of the intersection mesh line with the surface with the provided interpolation equations. In the intent of the NASA Lewis Research Center to provide similar setup code with the Rainer code is released. Surface panel flow codes can be used on trajectory impingement computation. However, the potential flow code with the simulate for the realistic surface of pressure for the distribution does not necessarily result in a realistic drop in impingement distribution. Large number of small panels of the water impingement region with a probably required with a curved surface and is represented by a series of flat panel droplets may see with the slope of the discontinuity to give it a distorted impingement distributions. Result can be expected with an improvement the number of the panels leading edge is increased with a special near the field computation method is used. The Vassaro code is candidate with a further development in conjunction with the water droplet trajectory analysis figure 3.4. The generally available with widely used reduced good subsonic flow fields with the NASA inlets. Those code with the singularity sources and doublets and were quadrilateral. 3.4 shows the surface panel modeling of the wing polyon nice lens Vassaro computer code. Panels in the piece were over the constant however limited to the subsonic flow of the icing frequently encountered higher subsonic transonic flight speed with the essence of the aircraft flying with the speed of the flying over the altitude with above the icing conditions. However, the ice analyzing with the range is still necessary because of the aircraft flying with low subsonic speed may still experience the sonic speeds of airflow into the engine inlet. Example during climbing. Droplet trajectory impingement code with the next of the analysis of the water droplet trajectory. A critical part with the analysis of the impingement of the information used to determine the ice accretion rates. Input required with the droplet trajectory analysis flow field over the flow of code liquid water content LWC over the air in the terms of the droplet side of the water mass per unit and volume. The following list of the drop trajectory codes selected using the same of the 2 criteria of those of flow field analysis. The Boeing 2D droplet trajectory, 3D droplet trajectory J.J. Kim, 3D droplet trajectory H.G. Normant. One of the strengths of the Boeing and the Kidd and Kim's that they are being compared to the data required by new experimental impingement testing carried out on the asymmetrical 3D inlets reference 314 ice accretion evaluation. 2 methods of determining ice accretion with the turbine engine inlets computer code analysis and wind tunnel test. The use of the computer code method the first step of the determine the free of the position of impingement water because of the use position of the ice being accreted. Because of the ice accretion altered with the shape of the inlet lip of the flow field must be recalculated to account with the new shape of the inlet computer code such as the Louis figure 318 when you with the predict ice accretion with the 2D airflow subsonic flow such as the 2D codes have within subsystem Sustained with empirical data with a tunnel test and study with literature have revealed no existing 3D icing acceleration accretion computer code. Availability, time, and cost, and particularly with the use of the analytical tools for evaluation accretion, with especially smaller with the aircraft, the company's alternatively empirical method of the ice accretion evaluation are available, although they're not necessarily recommended to research empirical to derive performance degradation equations based on many wind tunnel studies of the 2D airfoils, ice fragment drag. Suggestive but yet unproven method of the adapting droplet trajectory computer code previously described to the determination trajectories of the ice fragments from the ice of the surface, as described here with the adaptation of the because of the size of the shape of the shed of the ice are the different from the ice that is cylindrical water droplets, typically with the particle trajectory analysis. Path of the shed fragment is due to the balance of the gravitational drag force of the ice fragment. The drag force is calculated as the drag coefficient in the surface of the air with the fragment exposed to the airstream. Due to the irregular shape of the side of the shed of the ice for the fragment, specific drag coefficients have not yet been calculated. However, the taken into account with the ice fragment dimensions, the drag coefficient may be the estimated data of the drag coefficient, various body shapes. For example, the drag coefficient, a circular disc, figure 117, a line perpendicular flow direction. Thus, the drag efficiency, however, the hemisphere of varying 0.34 concave side away from the flow to 1.42 concave side facing the flow, because the ice fragments were tumbling about their own axis of the fragment was exposing area with the surface area fragment exposed to the airstream to passing airstream. The air can be modeled assuming to the tumbling of the ice presents since its ideal varying area of the airstream. The area of the surface fragment airstream is equal to 2 times pi of the geometric area of the drag coefficient, and the area surface area exposed to this airstream is now defined in a way that it can be used in existing particle trajectory codes. Based on this and the components impact of the shed ice that can be determined in turn with the potential structural damage these components can be assessed. Shows minimum area exposed, and shows the sensorial weight, a side view, and a four-way torque turning process, and then the front view fragment direction and cross-sectional area ice and fragmented presented airstream during tumbling. Worst case de-icing condition of the de-icing system such must perform satisfactorily throughout the range of icing conditions. Section discusses the worst case icing condition for various de-icing systems. Electrothermal system. Electrothermal de-icing system is controlled with electro-switching mechanism and cycle according with the program schedule of the design. Such a system follows Federal Acquisition Regulation Part 25 Appendix C icing envelope to determine the pre-ship of the power level, the timing cycle required with the various icing conditions. Extremely cold conditions required with a high thermal power level, the maximum cycle on the times precision. Even that cycle to become with a more critical ambient temperature increases since possibility of the generating water run back refreezing increase due to the thermal lag inherently in higher LWC with the reason ambient temperature just below the freezing generally represents the worst case condition for the electrothermal de-icing systems. Chemical system. Published information due to the chemical de-icer freezing point with the depression of the engine intake with the receptor parts due to the diffuse with any use of the tap of the system in the commercial aircraft with the turbo and engine inlet. Chemical system de-icing essential with a manner similar to the electrothermal de-icing with the breaking the adhesive the bond between the ice and the aircraft surface of how with no water will be generated, thereby eliminating the run back refreeze potential. The worst case condition generally with the ice surface of the adhesive of the bond and gray of the high adhesive of the bond generally related to the low LWC with lower temperature of the negative 14 degrees and 22 degrees, negative 22 degrees Fahrenheit, especially with the low MVDs of 15 microns. MVD is the droplet size measure of the medium voltaic diameter. Mechanical system. Mechanical de-icing system operating on a principle of shattering with the air accretion would typically operate best in the middle temperature range with the Federal Acquisition Regulation Part 25 Appendix C. Icing envelope, the code ice condition producing very hard brittle ice with each of the shell that usually result with a very thin ice accretion with doing the corresponding low LWC with the heat of the between the ice and the aircraft with the surface of the high and cold for low LWCs and low median voltaic diameter conditions. Even though the ice share of these conditions high, the heat of the bond reduces the shadowing since the accretions are thin, aerodynamically shaped. They should not have the significant effect of the inlet aerodynamics where the ice does share typically quite thin. Since mechanical systems become effective, some of the minimum thicknesses with the coldness highest icing conditions. Several of the de-icing cycle may be passed before icing becomes thick enough for de-icing to occur. using variable time de-icing cycles to provide solution with the coldest icing condition. The warmest icing conditions are difficult to mechanical de-ice for the icing conditions just below freezing. The ice accretion that must have the slushy consistency, since mechanical de-icers may shutter ice acceleration due to the effect of the slushy ice represents the worst case condition with high low LWCs found in warming ice conditions and ice accretions with a high and good de-icing performance as essentials. Engine manufacturer icing experiences measurement and shed ice fragments conducted with a major engine manufacturer the test inlet with a full side with approximately 8-foot diameter RB211 cowl in their barrel assembly that could happen and rotate with the icing airstream and allow with the air icing in a large portion of the inlet. During the electropulse impulse de-icing trials, attempts were made to collect the pieces of the shed ice to measure their size. This is only partially successful because it's never clear whether the collected pieces actually have been shed with the size at the site they were found, whether they broken in a flight during impact with the catch, or the conclude the only definite way to determine shedded ice fragment was to photograph the ice during the immediately after shedding. High-speed film video cameras of 400 frames per second mounted just above the front of the inlet with a focus of the region of the inside of the inlet barrel with extend of the inlet leading edge to about 3 feet rearwards. This section painted back to the 2 by 2 inch white cross. The black paint was intended to improve the visibility of the ice fragments so that they're being shed with the white cross could be used for reference to the estimating of the fragment size. It was found that the trajectories of the lost ice fragments brought with the fragment toward the camera with the well back through the inlet, making them appear large relation with the white cross of that than they actually were because the actual trajectory was known. Not known, no correction could be made for this effect with the fragment size of the estimate could only be made during the short period immediately after the ice has been shattered or before the trajectory brought it away from the inner barrel. This experience led with a possible technique improved the method to determine the fragment size of the shed of the ice. Instead of 1 camera, 2 cameras should be used with the pointing of the orthogonal direction. In this case, just described, for example, the second camera mounted on the first camera pointed downward would be the entire background inlet, inner barrel, wing surface, and etc. should be painted black to make the ice fragment with a more visible continuous grid, which should be used instead of the white cross that makes size of the measurement easier. Camera speed typically from 300 to 1,000 frames per second should be chosen according to the speed of the airstream of the air around the inlet. Using the above technique to measure the ice fragment size, possible trajectories may provide empirical necessary to substantiate future shed ice fragment trajectory computer codes. Safety requirement substantiation.